Okay, I think it's time to start now. So, welcome everybody. Thank you for tuning into my latest talk, which is about confabulation, Capgras, and Cotard syndrome. And I'm going to be trying to tell you about the amazing insights that we get from studying different types of brain disorders. So as an outline, what I'm going to do is first of all tell you about the jigsaw of cognitive neuropsychology, because this is about the rationale of how we study individuals with brain damage to try to understand normal functioning. Then I'm going to tell you about what I call the road less traveled, because whilst neuropsychology is one of the rarer aspects of psychology, there are aspects even within neuropsychology that are very rare compared to the rest. And I'm going to illustrate that to you in some ways, because that's what this talk is about. It's about the disorders that are rare, but which give us great insights into the functioning of the human brain. I'm going to start with telling you about the division of labor. And this is to do with the fact that our two hemispheres do slightly different things and how they need to cooperate. And the way we get this understanding is by a very rare disorder known as split brain syndrome. Then I'll tell you, we'll move into faces and how by studying people with rare forms of face recognition disorders such as prosopagnosia, Capgras, and hyperfamiliarity for faces, we again get an insight into this skill that we take for granted, but which is extremely complicated. In the same way, I'll move into the skill that we all use and have to use for daily survival, which is memory. And the best way, or one of the best ways to demonstrate the complexity of memory is by showing you when it's gone wrong. And I'll tell you briefly about the 7 sins of memory, then tell you a bit about a couple of different conditions which demonstrate the complexity of memory. Now, the confession I had to make was that, in fact, I'm not going to be talking about Cotards today. The reason being that as I started developing this talk, I kept finding more and more interesting subjects that I wanted to tell you about. And rather than skip through everything at breakneck speed and not really give you any depth, I decided that it was better to split the talk into 2. So part 2 of the talk, which will be in 2 weeks' time, will go through some more amazing disorders. And the first part will be about how we pay attention to the world. And we get amazing insights from something known as unilateral neglect, where sufferers of this condition ignore half the world. And I'll tell you about anosognosia, which is about ignoring pain and not even acknowledging it. Then something about our physicality and our awareness of ourselves physically. And so I'll go into this section that I'm calling I Am What I Am, talking about phantom limb syndrome and a very bizarre thing called the alien hand sign. Then just before the end, I will start speaking in tongues and tell you about foreign accent syndrome, which is a disorder of language, which is quite rare but interesting. And then finally, I will end, as it were, with existing, with Cotard syndrome, which is a bizarre condition where an individual believes that they're dead. So there's lots to look forward to in the talk in 2 weeks' time. So I'm going to start off with why we look at damaged brains if ultimately, as a psychologist, a cognitive psychologist, I'm interested in how normal brains, yours and mine, functions. And a bit of this is recap from one of the first talks, but I know that we've got new listeners, so do bear with me while I just cover this again. This is one of my favorite quotes, which really beautifully exemplifies what cognitive neuropsychology is, and it certainly means a lot to me. This quote from 1943 is that in any well-made machine, one is ignorant of the working of most of the parts. The better they work, the less we are conscious of them. It is only a fault which draws attention to the existence of a mechanism at all. And so this quote is about the fact that in our everyday lives, we use so many different types of machines, computers, cars, things in the kitchen, etc. But unless you're an engineer, a designer, etc., you don't need to know how they function. It's only when one of them goes wrong that you start understanding the complexity. So you don't need to be a car mechanic to understand how a car functions. And it's only when something goes wrong with a car that you're driving that you start understanding things about things called the gearbox, the fan belt, the cooling system, etc. So this is the kind of rationale that we use in cognitive neuropsychology. And I've come up with my own way of looking at this, which is that cognitive neuropsychology is recreating a broken jigsaw. So if we want to study something like human memory, which for the sake of this, I was going to say it's a black box, but for the sake of this white background, it's a white background, white box, which is extremely complicated. And what we're trying to do as cognitive psychologists is to understand what's inside this box and the inner complexity. Now, this box might be made up of 9 interlocking pieces, like a jigsaw, 9 very complicated pieces. It's way more than 9, but for the sake of argument, let's say 9 pieces. Now, one way we can try to study it is by studying it while it's functioning fine. So a lot of cognitive psychology involves doing research with university undergraduates and the general public to try to understand the mechanisms. But the way that cognitive neuropsychologists do this, and the way I do this, is by studying people who are missing a part. So if I meet a patient who's got a particular memory problem, what I'm trying to do is just study that one missing part, the white part that you see there. And by studying that patient in depth, I can eventually work out what one part of this complicated jigsaw is, because it's like studying a broken car and understanding that there's something called the fan belt, and just understanding the fan belt when that car's not working. So now I've got an understanding of one part of the jigsaw. Now, if I met a patient with a different type of memory problem and I studied that patient, I would end up understanding a second part of the jigsaw. And the idea is that by studying lots of different patients in great depth, what we eventually want to do is to understand the whole of human memory. And we've done that by studying many broken down versions of it, with each of our patients giving us an insight into how one of the complicated interlocking parts works. So that is the rationale that we use in cognitive neuropsychology. Now, I wanted to demonstrate to you how rare the conditions are that I'm going to be talking to you about today. So this is a graph that one of my students, Diego, has created for me, which is the number of publications, which is on the y-axis going up and down on the right-hand side. And on the x-axis, we've got the year of publication going from 1960 through to today. And if we look at something like amnesia, memory problems, which is an area that I work in, we see a nice graph there. Slowly over time, that there are more and more papers up to the point where, on average, there are about 450 scientific papers published a year to do with amnesia. Then if we move to aphasia, which is a language disorder caused by different types of strokes, and also a disorder that happens with aging, what we see is a similar pattern. And then maybe in about 2008, things really took off. And so now there are about 700 to 800 papers a year in aphasia. So those are 2 of the most common areas that are studied. Whereas if we look at Capgras syndrome, one of the conditions I'm going to be talking to you about today, we see that it's virtually flatlining because it is so rare. If we look at split brains, we see not much there either. We look at confabulation, one of the memory disorders. We see not much going on. Psychogenic fugues, you can't even see it because there are so few papers. And then hyperfamiliarity for faces, again, so little. So the main take-home message from this graph is that we have conditions like amnesia and aphasia, which are relatively rare compared to, let's say, depression or mental health problems, etc. But in the world of neuropsychology, they're the big hitters. Whereas the conditions that I'm going to be talking to you about today, Capgras, split brain, confabulation, fugue, and hyperfamiliarity, those are ones where there's very little work. And most of this is to do with the rarity of these particular disorders. Now, what I want to do is first of all start with hemispheric specialization to show you how we've developed an understanding of what the two halves of our brain are doing. So this is a dissected human brain. On the left-hand side there, you've got what is actually the right hemisphere. So it would be as if you've taken this part of my head, and on the right-hand side, you've got my left hemisphere. So it'd be that area. So the bit at the bottom pointing down in each figure or each picture is the front of the brain over here. And the bit that is highlighted in red with the red arrow, that kind of white tract, as we call it, is known as the corpus callosum. And the corpus callosum is an extremely important area of the brain. And the reason for that is that the two parts of the brain are actually separate. So you could actually slide something in between the two halves of the brain. And the corpus callosum is the great mediator between these two. So effectively, we've got things going on in our two hemispheres, and there's a tract of fibers that goes in between the two hemispheres to connect them to one another. And we understand the complexity of the corpus callosum by looking at patients who've got certain types of disorders. Now, I've just got to check whether me hitting the microphone caused a problem. I don't think it has. No, it hasn't. Okay, so to demonstrate what the corpus callosum is doing, in this figure here, what you've got is the left and right hemispheres in the diagram at the bottom. The front of the head is at the top, and you've got the two eyeballs, and then the back of the head. This area here is where we first start seeing things in the world. And importantly, if this imagined cartoon person in the middle at the bottom was just staring straight ahead, right in front of them, what would happen if there was a cat on the left side of the world and a dog in the right side of the world, is that the image of the dog would go into their two eyes, and that image would go exclusively to the left hemisphere, and the image of the cat would be taken to the opposite side, to the right hemisphere. And it's very complicated. The main thing is that if I'm staring straight ahead like this, then everything to my left will go to my right hemisphere, and everything to my right will go to my left hemisphere here. Now, we don't notice this because we move around like this, and our brain actually puts all of that information together, and it can only do that by the corpus callosum. So the corpus callosum takes the information from here and adds it to the information from here, so that you get one unified view of the world. Now, we know this because of the damage that can happen and the disorders with split brain syndrome. Now, just to demonstrate what is happening here, this is a video of Alan Alda from MASH trying to do a task.
I found out how true that was right away when I was asked to draw a different shape with each hand. In a brain like mine, roughly speaking normal, at least all in one piece, the left half of my brain controls the right side of my body, while the right brain controls the left side.
Oh, no.
But because the two halves are connected,
Nothing wrong with that.
getting each hand to work independently isn't easy.
Well, we're saying that the fact that Alan's hemispheres are connected, and that the motor messages from one are confusing the motor messages in the other.
I was just drawing an upside-down duck.
Okay, so what you see there is that he's shown two shapes in the two hemispheres. And the way that this is done is by making someone stare at the center so that we can control what goes into the right hemisphere and the left hemisphere. And because his corpus callosum is there, the corpus callosum is taking that information from the two halves and pushing it together so that he sees one thing, and then his two hands are trying to draw those two objects separately. And not doing very well on it. Now let's look at this man called Joe, who suffered from very bad epilepsy. And epilepsy is an extremely complicated disorder, and I'm not going to try to explain it, but it's an electrical storm of sorts. And depending on how bad it is, sometimes what's happening is that the electrical storm is shuttling from left to right brain, but it's going via the corpus callosum. So what happens is that a person's control of their body, their breathing, their swallowing, everything can go, and so their life can be at risk. So if the epilepsy is bad enough and it is moving through the corpus callosum, then this very extreme surgery was created known as colossotomy. And that involves actually cutting the corpus callosum so that the highway for those signals, which usually are good, but if you've got bad epilepsy, it's also moving the epilepsy between the two hemispheres to stop that. So effectively, what's happened is that by cutting that corpus callosum, Joe's two hemispheres are left independent of one another. First of all, I wanted to show you someone else, which is myself. Now, the reason for this is that when I worked in the States, I worked with Antonia and Hannah Damasio, and Hannah Damasio is one of the top brain imagers in the world. And when she found out that I was an identical twin, she asked if she could image our brains because she wanted to see how similar our brains would be. Now, in the top panel there, you see my twin's brain. And it's, again, a section so that on the left-hand side there, you see as if we'd cut down the middle of Frid's brain. So you see his right hemisphere, and on the left-hand side, you see his on the left-hand side, you see his right hemisphere. The right-hand side, you see his left hemisphere. Now, on the bottom layer, you see my brain. And the important thing is that if you see that bit right at the back of the corpus callosum, it's got this knobbly bit. So it looks like a fat C on its side. When you look at my brain, what you see is that this doesn't exist. And unfortunately, when they saw this, they actually got a bit concerned. So this was done just for fun in a way, to see if two identical twins' brains would be similar. And what they saw in my scans got them worried because that looked like it could be a tumor. So given that I work in brain injury and look at issues to do with brain damage, I was rather concerned. Thankfully, I got scanned again and they found out that I don't have brain injury, but tumor, but I've got what's known as callosal agenesis, which is where the back end of my corpus callosum hasn't actually formed properly. And the reason that I'm mentioning this is because that is the area of the brain which connects the visual two halves of the world. And someone known as Michael Corbolis, when he found this out, he was rather interested in me because he's trying to look at research, do research on people like myself. And what he's done is done research on me and compared me to my identical twin, and found that my visual attention is very different to normal, and it's even different to my twins. And it's as if my visual attention is actually stuck in my two hemispheres. I'd be happy to describe that to anyone if they would like later on. So I've been a neuropsychological case study myself.
Okay. But when Joe is given the same task, his two hands operate as if controlled by two separate brains. What's happening is that each half of Joe's brain is given a separate instruction. He's asked to fix his eyes on the cross in the center of the screen. Anything flashed to the right of the cross goes only to his left hemisphere. Things to the left go to his right hemisphere. Because the two don't communicate, each hand does only what its half of the brain sees.
Wow, look at that. It's really like two different people doing the same.
That's right.
Same task.
That's the idea.
So there's something going on there, whereas Alan Alda had the problem where his two hemispheres can talk to one another and his hands are effectively working together. It was difficult for him to draw those figures. Whereas here, what we're going to see is what happens with Joe, because there is something going on between the two hemispheres, and it's best to see the video itself.
Okay, Joe, I want you to keep your hands out in front.
In an experiment that's now a classic in brain research, Mike Gazzaniga over 30 years ago used a similar setup to find out if the two halves of the brain are specialized to do different things.
Ship.
Joe is being flashed a word only to one half of his brain. Words flashed to the right
Storm.
are seen only by his left brain, and Joe can report seeing those words just fine.
Piano. Good.
But when a word is flashed to his right brain,
Didn't see that.
Okay. So I'm going to ask you
but now watch what happens.
to draw that with your left hand.
I'm gonna be lost.
Why don't you try drawing another picture of it over here if that'll help you.
Oh, phone.
Oh, okay.
It's almost as though somebody has given him a secret communication.
That's
and
right.
Now he knows that it's a telephone. Up until then, he was blind to it.
Exactly.
When Gazzaniga first did this experiment, it instantly proved that the ability to speak resides almost exclusively in the left hemisphere.
Big door.
Not until he sees what his right brain is drawing is Joe able to name
We
it.
said church, didn't we? After looking at the picture.
But he had to figure it out about as long as we did. That's really interesting. It's a picture here of somebody communicating almost with another person.
And the communication is not occurring inside the head, it's occurring out on the piece of paper.
Yeah.
So what you see there is that when the word piano was on the right-hand side, it was going to, as I was explaining before, it goes to the left-hand side of the brain. Now, the left-hand side of the brain is the speaking part of the brain, because language is also in the left hemisphere. But when the patient sees the word phone on the left-hand side of the center, that goes to the right hemisphere. Now, to read that word, you need to send that information to the language center over here. But because the corpus callosum has been cut, he's not able to do that. So the result of that is that the patient says, I don't see a word. But when he's asked to draw it, he actually can draw something that looks like a phone. And so what that suggests is that there's some understanding happening within the hemisphere, and we still don't understand what's actually happening, but we do know that there's some information going through, but it's almost as if that hemisphere is mute to the word itself, but it's showing an understanding of what's there. The next thing I wanted to do with that same patient is a remarkable experiment that the scientist there did. Now, the scientist, I should have said, is called Michael Gazzaniga, and he's one of the most important people in the world in cognitive neuroscience, and he's a specialist in these split brain patients. And what he did was he used paintings like this by a Renaissance artist called Arcimboldo, who was on some good drugs, because Arcimboldo had this thing about drawing paintings or doing paintings using everyday objects. And here, this is a painting of the one of the Austro-Hungarian emperors, and this one is called Rodolfo. And I'm sure I don't need to convince you that there's a face-like structure there, but it's made up of apples and pears and cherries and flowers, etc. Now, the reason this is important is that we can see this this image both as a face and as fruits and vegetables. But let's see what happens with Joe. So this is Joe being shown that images like the one I've just shown you by Arcimboldo, but they're going to go to separate hemispheres. So let's see how they do that.
The first painting goes to the right hemisphere. And Joe points to face. The next painting goes to his left brain. And this time he points to fruits. Mike seemed pleased. Are you having a moment?
This is too good.
Again to the right brain, and Joe sees it as a face.
Point it down.
But to the left brain,
Face made out of books.
Point it up.
Put it in the books.
were you happy with what you're seeing?
It's unbelievable. He's doing it. You see that?
It's because it's going so fast, it's shifting from left to right so fast, I can't keep up with you. You're used to looking at this.
When you show him a face in the right side, the left hemisphere,
Yeah,
he's focusing in on the elements that made up the face.
yeah.
When you show him the exact same picture in the left field, going to the right hemisphere, he's focusing on the face and not the elements.
And not the elements.
So what we see is this really amazing finding that the left hemisphere sees the same thing in a different way from the right hemisphere. And what that helps us see is that when the painting is sent to the right hemisphere, he sees a face. When the painting is sent to the left hemisphere, he sees the vegetables or the books or whatever that make up the painting. And what that tells us is that the right hemisphere is possibly specialized for seeing human faces. And this is something that we know anyway from studying other types of patients. But this is a remarkable demonstration that the same patient can see the painting in two different ways. If the right hemisphere sees it, he sees a face. If the left hemisphere sees it, he sees the parts, whether it's the vegetables or the books, etc. And that's going to then allow me to move into what we see in a face. So to start off, I'm going to show you this video of a patient that I worked with to give you a sense of prosopagnosia, which is a condition with involving face recognition problems.
Uses things like people's clothing, whether they wear glasses, whether they've got a goatee, etc. So he tends to use information that's classically outside the face.
Everything about you, I can see. Your rimless glasses, your shirt colour of your hair. But it's just putting the facial bits together is difficult. I have difficult describing anybody's face, even though I can see it perfectly.
When David does the same test I did, he fails to recognize even the most famous of faces.
And here,
I haven't got a clue. I should know who he is. Gordon Brown or Prescott. Face doesn't.
But then a photograph brings a reaction.
Is that my wife? Yeah.
okay, David, when you saw this photograph, you had a bit of an emotional reaction. So what was the reaction?
I wasn't sure if it was her. I wasn't sure if it was Val. And I'll get disappointed if I was wrong.
Yeah.
Because I should be able to recognise the most important person in my life.
Yeah. So what you see there is my patient David, who had a massive brain hemorrhage, and that brain hemorrhage nearly killed him. Thankfully, he survived, and after his brain had started healing, most of his problems went. But he was left with this one problem, which is a really dense inability to recognize faces, including his wife's, as you saw in the video. And David's brain damage is in this area over here. So what we see is that with Joe, whose hemispheres are okay, but the two halves can't connect to one another, if you send information like that painting to the right hemisphere, he can see the face. Whereas David, he can see the face, but he can't recognize it. And so we've got evidence from two different sources there that the right hemisphere is really important for recognizing faces. Now, what we found with certain patients with this condition called prosopagnosia is that, in fact, they don't have no recognition. I know that's a double negative, but I'll explain what I mean to you. My former bosses, Daniel Tronell and Antonio Damasio, they did a really interesting study with two patients that they had who had prosopagnosia just like David. And what they did is to present the patients with photographs of people who should have been unfamiliar, so strangers, and family members that the patient should know if they didn't have any brain damage. And they showed them the photographs of these people, and they asked them just to say, on a scale of 1 to 10, even though they didn't recognize them, could they just say whether the face looked vaguely familiar or not? And this is what both patients said for the unfamiliar faces, so the Joe Bloggses that they shouldn't have recognized anyway, so about an average of 5 out of 10. And then for the pictures of their own families, patient 1 was the same, and patient 2 actually found the pictures of his family even less familiar than unfamiliar faces. So this is classic prosopagnosia. You and I would see family members and say, yes, 10 out of 10, that's someone that I know. And unfamiliar people, we might say 4 or 5. So there'd be a real difference. The red bars would be at 10 and the blue bars would be much lower. Whereas for both these patients, we don't get that at all. But what Dan and Antonio wanted to do was to see whether they could see whether there's any recognition in a different way. And the way they did that was using what's known as galvanic skin response. And galvanic skin response is a measure of how much sweat there is on your skin. And this is to do with what's known as an autonomic response, which is a biological response. It's got nothing to do with the verbal responding, etc. So it's more of a visceral reaction. And this is the kind of thing that's used in lie detector tests, because if we get excited or if we're nervous or frightened, then certain systems within our body tense up and we get sweaty. And if we get sweaty and we pass a little electrical current over our skin, then because electricity runs more quickly in liquid, then the electricity will run more quickly. So basically, if you're completely calm, electricity runs at a particular speed because your skin is dry. If you're nervous and you're sweating, then because electricity runs more quickly through the sweat, that electricity will run more quickly and will be able to tell that you're sweaty. So that's what's used in lie detector. So this is what Dan and Tony used. And the galvanic skin responses they found when they showed these unfamiliar faces, which, remember, the patient said 5 out of 10 they didn't recognize at all. So this was as if, yeah, I don't care, it doesn't do anything for me. But when they showed them the pictures of their family members, this is what the galvanic skin response was. So both of these patients, although they show no what we call overt sense of familiarity, which is the graph on the left-hand side, they don't show any real difference in response overtly. When you look at their biological response, we see a much deeper response to family faces. So what that suggests is that although they say, no, don't know who this person is, somewhere within their system, there is some sort of recognition going on. It's just not getting to a conscious level of awareness. And that's rather interesting because of the condition known as Capgras Syndrome. And Capgras Syndrome involves the lack of conscious recognition. And it's actually the opposite of what I've just told you. So whereas with the prosopagnostics, they don't know who this person is, with these people, they can't feel who the person is. And they end up feeling that their close family members have been replaced. So this is a video of a patient called David, and you'll see what happened to David after his car crash.
2 years ago, David was involved in a terrible car accident while driving back to California from Mexico.
There was a problem with the car, and I landed in the highway with my head first.
Okay. Like this truck that is coming by?
For 5 weeks, David lay in a coma. Serious injuries led to the loss of his right arm, but to everyone's relief, when he regained consciousness, his mental capacities seemed to be intact.
He was articulate, he was intelligent, not obviously psychotic or emotionally disturbed. He could read a newspaper. Everything seemed fine, except he had one profound delusion. He would look at his mother, and he would say, "This woman, doctor, she looks exactly like my mother. But in fact, she's not my mother. She's an imposter. She's some other woman pretending to be my mother."
The injury to David's brain had brought on a very rare condition called the Capgras delusion.
I was cooking dinner, and he probably didn't like the food that night. Okay. And he said, "You know, the lady who comes in the morning, she cooks much better than you. Okay. It's that lady. I like that lady very much." Okay. But the lady was me, of course, all the time.
David was also convinced that his father was an imposter.
He would say to his dad, "You know, I'm sure you would like to meet this guy. He's so much like you, but he drives better. He doesn't go so fast."
It can look identical to him, exactly like him, but it's not him.
So what you see there is this remarkable condition where this young man, when he's with his parents, he thinks that they've been replaced by imposters. And he says he looks exactly like him, but he doesn't feel like him. And Capgras syndrome is very rare, and it's usually to do with people, and it's close family members. It's not about the milkman or the postman. It is about very close family members. Apparently, there are cases of animals as well. So there is a case study where someone said that their cat had been replaced by an imposter as well, and of people's homes. And in fact, in the video, if you wanted to find this video, it's called Phantoms in the Brain. David also claims that he's not in his own house, but they always say that it looks exactly like their home, but it isn't their home, it isn't their mother, etc. But it's only when they see them. If they're talking to them on the phone, they're completely okay. So there's this really odd thing going on where they say they're acknowledging that the person looks like their parent, but claiming that they're not. Now, a way to understand this is that in normal face recognition, what happens, and in this graph here, in this diagram here, what we have is, again, the face as if you're looking at it from over here. So the front of the brain is on the left-hand side. And you see the visual cortex on the right-hand side. So any information comes to the back of the head to begin with. And what happens is that when you see me or someone you know, that information starts off at the back of the head and it starts getting processed along what we call the ventral route, along the floor of the brain. And that is seeing the edges, seeing the color, seeing the shapes, and everything is put together. And at some point, that information that is being transmitted from your eyeballs is turned into an image. And that image is what you're seeing right now. Then what human memory involves is saying, okay, this is what I'm experiencing right now in front of me. Is there a record in my memory systems, in my hard drive somewhere, that looks just like this? And so your brain looks for anything that looks like this image that you're seeing right now. And when you get a match between the two of them, at that point you say, aha, I know who this person is. And then you go on to say, okay, that's that Indian guy from Britain who does those lectures online, and his name is Ashraf Jansari. So there's a staged process where you first of all form the image, which is your sketch of what you're seeing. Then you link it to something that's in your memory system, and then you add information as you go along, working out who I am. So that's what happens under normal circumstances. But what these patients with the Capgras syndrome and also the patients with prosopagnosia who show that unconscious awareness show us is that there's another type of recognition that's going on. And it's that yellow route that you see in the figure, which goes further through the middle of the brain, through older parts of the brain, which are giving us a more emotional reaction to what we're seeing. And that emotional reaction is, yes, this feels familiar. I don't know why, but it feels familiar. And for our loved ones, the ones closest to us, we get that emotional reaction of, I like this is familiar, it feels safe, love, etc., etc. And that feeling is really important for when we're near our loved ones. So the idea is that when you see someone, you're getting these two different processes going on. One, which is the visual recognition, which is going along the floor of the brain, and the other one, which is going through the middle, older part of the brain, is a more emotional reaction. So that's what you and I get if we don't have prosopagnosia. If we have prosopagnosia, like the patient David, who has damage along this section of the brain, then that damages that overt recognition system that's going along here. And so the patient doesn't recognize his wife, etc. But then, as you saw with the patient studied by Dan and Tony in the States, they say, no, this face doesn't look familiar, this face doesn't look familiar, etc., whether it's a family person or an unfamiliar person. So that was the graph that was on the left-hand side. But when they're asked to just look at the faces, the galvanic skin response, which is about that emotional response, that's working fine because they don't have damage in that section of the brain. So that's why they showed this emotional reaction with the skin response, even though they say, I don't know who this person is. Whereas with David, the young man in the video, what's happening with him is that his damage is in a different part of the brain. All of this is completely intact in David. So when he sees his mother or his father, he creates the image that's in front of him. Then that gets processed, and then his brain says, okay, I'm seeing this in front of me, this person. Is there an image in my head of someone who looks like this? And he finds this image, and it's an image of this woman that he knows. Then he realizes it's his mother, and that's what that system there is telling him. But when we see our parents or our loved ones, we also get that feel-good factor and that warmth. And because the damage in David is to that older emotional system, he's not getting that. So he's not getting that feel-good factor. So what he sees, this system is telling him that this woman looks like my mother. But what he's feeling is nothing. He's feeling it as if he's seeing a stranger. And so that's why his brain somehow says, there's something not quite right here. The only way this can be possible is if my mother has been replaced by someone who looks like her, because it just doesn't feel like her. So we have this incredible insight into how our recognition of our loved ones involves not just a visual recognition, but this emotional recognition as well. Now, almost the opposite of all of these is known as hyperfamiliarity for faces, and this is even rarer. And in this condition, unfamiliar people look really familiar, and the individual says that lots of people feel familiar, and yeah, I know that person, I know that person, I know that person. Now, it's an area that I know almost nothing about, but these brain scans of a particular patient that's been studied show an area in the left hemisphere, that area that's being pointed in the top brain scan, that looks a bit more white than the area around it, which is somewhat damaged. And with the patients that have shown this hyperfamiliarity for faces, they tended to have epilepsy in this area of the brain, which is the temporal lobes, which is involved greatly in face recognition. Now, what we see is that if we get damage in the equivalent area on the right-hand side of the brain, then you have a recognition disorder like my patient David, who was in the video. It's a bit confusing because there's my patient David and the young man David with Capgras. But my patient David has got damage over here, and therefore, and that's resulted in prosopagnosia, not recognizing his wife. Whereas these people with the hyperfamiliarity for faces, they've got an abnormality on the left-hand side of the brain in the same area. And what's happening for them is everyone looks like they're familiar, even strangers. And as I said, this is a rare condition, so not much is known about it. But the parallel and the difference between these two types of patients, the ones with prosopagnosia and the ones with this HFF, and both of them got damage in the temporal lobes, but one in the right side, which is for face recognition, and the other in the left side, which is suggesting that something is going on in the left-hand side of the brain as well. So now I'm going to move into memory and forgetting. So what is memory? What is forgetting? And do we all forget? Now, these are enormous areas, and I'm not even going to try to tell you the answers. If you're interested, then you should have a look at this wonderful book by one of the gods of this area, Dan Schachter, and he's written this book about the 7 sins of memory. And Dan Schachter works at Harvard University, but he did his PhD with the godfather of memory research, known as Endel Tulving. And at some point, Dan decided that if he thought about all the different ways that memory goes wrong, there are 7 different things that go wrong. And I'm not going to go into them just because it's a huge topic. But what I'm going to try to do is to demonstrate some of that in the next 10 minutes or so. Now, this is a video, it is 2 minutes long, but it's a marvelous video because it brings together a lot of really important things about the fact that memory is not what you think it is. Memory is not a recording of what's happening right now. Memory is a set of images that you're storing, and then when you try to remember it later on, what you're doing is you're trying to reconstruct what could have happened, and sometimes that goes wrong, and that's what forgetting is. So here we go with the video.
In fact, there's more than one kind of memory. When we talk about memories of events, we're talking about episodic memory. We create episodic memories by encoding sensory information from the world into our brains. These become memory traces, which are stored until they are retrieved, a fancy word for remembering. However, you don't remember things exactly as they were. Memory is constructive. Each time you remember a memory, you're actually rebuilding it using those memory traces and your own guesswork. That's why psychologist Elizabeth Loftus compares memory to a Wikipedia page. You can edit it, but that means other people can too. And they're not always right. When a memory is distorted by wrong information before it's retrieved, this is known as the misinformation effect. Literally hundreds of studies have shown the misinformation effect. In one study, Loftus and her colleagues showed people slides of a car accident. Then, they asked the participants questions about the scene. Some were given a question with misleading information that mentions a yield instead of a stop sign, while some saw a question with consistent information. Later, those who were misinformed were about 20% more likely to incorrectly report that they saw a yield sign compared to those who received the correct information. Taken to the extreme, misinformation can send an innocent person to jail. You wouldn't want to be in a police lineup with a misinformed eyewitness. Eyewitness memory is easily distorted if there are suggestive police procedures. For example, if a police officer unintentionally implies that the crook is in the lineup. When witnesses talk to each other, they also share information that might not be true. Despite this, many jurors and judges are convinced that eyewitness evidence is the most persuasive kind of evidence out there. This has serious consequences. Out of the 314 prisoners who have since been proven innocent, almost 3 out of 4 were mistakenly identified by an eyewitness. Although no one is immune to the misinformation effect, young children and the elderly are the most prone to it. In addition, the effects are strongest after a long period of time, when the memory trace becomes so weak that we rely almost entirely on external information to reconstruct the memory.
Okay, that video picks up on a lot of really interesting points. The first is that memory is not this collection video series that you can just go and play again. Memory is a reconstructive process, and you try to work out what could have happened. And a lot of the time that is right, but it's not infallible. And errors can creep in, and some of those errors are talked about by Dan in his book. And we see that this happens in lots of different ways. And the work by Elizabeth Loftus, who I think Time magazine had, or the American Psychologist had a poll on the most influential psychologists of the 20th century. And she was the highest ranking woman in it because her work on eyewitness testimony about those stop signs, etc., has evolved into this massive thing about how memory is very fallible, that lots of things that are said in court are not the gospel, let's say, and that there are lots of errors going on. And we saw that with the Innocence Project. This is a project to try to exonerate people who've been committed of crimes where DNA evidence has shown that they couldn't even have been there. A lot of the problems that have happened with these wrongful convictions have been because of eyewitness testimony and because of eyewitness identification of people. And in fact, Diego, who's helped me with a lot of the videos, etc., for today, his PhD is on eyewitness testimony and the fact that it's very fallible. So we've got lots of different things going on there. That memory is very, it's complex and it can go wrong at lots of different levels. And an important thing is the fact that we're not all the same. And I showed this diagram for my FACES talk a couple of weeks ago. And this is the famous bell-shaped curve, which is about the fact that in anything to do with nature, heights of trees, our running abilities, etc., what we tend to find is a spread of different abilities, heights, etc., etc. So let's take height as an example. If we measured height, then I'm very bog standard, boring, right in the middle because I'm 5'10" and that's about average height for a male. There are some people like my friend Andrew, who's much taller than me, so he'd be on the right-hand side of the curve. And then there are other people that I know who are shorter than me, and they're on the left-hand side of the curve. So this is just part of nature. And what we find in face recognition, in heights, etc., but also in memory, is that we're not all the same and that we vary a lot, with some people having really good memory, some people having poor memory. And a lot of that is to do with the distortions that can happen in human memory. Now, an extreme example of this is known as HSAM, or highly superior autobiographical memory. And this is people who have exceptional memory from their lives. And this is a graph from a study that I found, which is 4 people who might have this, what's known as HSAM. And they were given dates from any time in the past and asked to say what they were doing at that time. And compared to them, we have in the gray bars controls, so people who don't claim to have exceptional memory, and they were trying to work out what was I doing on the 12th of February 2012. So that's what the dates quiz is. You give a date and you ask the person, what were you doing, etc., and then you can give a score for that. And what you see is that the regular controls are pathetic. because most of us don't remember exactly what we were doing on the 12th of February 2012. But these HSAM people, the lowest scoring one's got about 70%, and the highest scoring one is 90-something%. So these people have got exceptional memory of things that have happened in their lives. So they're at the extreme right hand of that bell-shaped curve. They've got extremely good memory. One thing I would like to say at this point, and I've had this, let's say, debate rather than an argument. I've had people say to me that these HSAM people never forget a thing in their life and that they remember every day of their lives. That is patently not true, because all 4 of those white bars are less than 100%. If someone could remember everything that they'd ever done in their lives, then all 4 of those bars should be at 100%. Now, those 4 people have got exceptional memory, as we can tell by comparing them to the 4 controls in the gray bars, but they do not have perfect memory. And it's something that really gets my goat when people talk about super recognizers as remembering every face they've ever come across, or these HSAM people remembering every moment of their lives. It is just not true. They're just much better than you and I. Okay, moving on. As I said earlier, memory is a reconstructive process. And so that reconstruction involves you thinking about what could have happened. So taking the example of 12th of February 2010, what your brain would do without you being aware of it is think, where was I living in 2010? February, that's during the winter. In my case, it's because my birthday's on the Valentine's Day, 14th of February. So this will have been 4 days before my birthday. So where was I living 10 years ago? So what will I probably have done 10 years ago? And that's what's happening in the background without you being aware of it. And then you output a memory, and then your friend might say, no, that happened in 2012. In 2010, we did something different. And so what happens is that this is what was shown in the video, that by talking to other people or reading our diaries or whatever, we get some sort of idea of how close we are. Now, we get a beautiful insight into how this can go wrong with a disorder called confabulation. Now, this is a brain scan of a patient that, again, my former bosses, Tranel and Damasio, worked with. And it's a very hazy brain scan. And if you were at my Neurobolics talk a couple of weeks ago, you'll know that I rail against showing brain scans for the hell of it. But the reason that I wanted to show this is just to demonstrate that this patient did have brain damage. The clearest figure is the number 2, the top right one. And you see the area of blackness, especially in the front of the brain. So the top of the slide, the top of the image, which is the front of the brain, and then going further back on the right and left-hand side. That was caused by a particular type of brain damage he had, which was a rupture of an aneurysm. But I won't go into what that was about. The reason that I want to tell you about this patient is because I worked with this patient when I lived in the States, when I worked for Tony. And this patient was a confabulator. So he was a postman, an Iowa postman, but he claimed to have been at the funeral of the president of Egypt. He also claimed to have been the commander of the Space Shuttle. Now, both of those things could have been possible, but he was an Iowa postman. And the research I was doing with him was an attempt to try to see what was going on here. And it was quite heartbreaking because he during the work that I was doing with him, he told me that he'd had alien visitations, and the aliens had done certain tests on him. They'd taken him to their ship, they'd taken semen samples from him, etc. And he believed this as if this was complete truth. And he even asked me if I would hypnotize him to see how true this was. And I said, well, I can't do that because I can't hypnotize, and I don't think it's ethically possible anyway. But he really believed in it. It wasn't just flight of fancy. Now, with the research that I was doing with him, I developed a task where I gave him some stories to remember, and then I looked at how he remembered these stories. And what I found is that he'd come up with what seemed like magical stories, but in fact, each of his stories was little bits of this and that added up together. And I think that what happened in this patient is that the brain damage affected his ability to tell reality from things that he'd seen on TV, etc. And he was combining these in a way where a headache to him, having watched X-Files, etc., must have been because of alien visitations, etc. And so his brain outputs this potential candidate memory for my head must be hurting because those aliens, they do come down and they drill into your head, etc., etc. Now, it's a complicated disorder, but this insight from confabulation shows us that when we remember something, we're creating a hypothesis of what could have happened. And by and large, we tend to be okay. But I bet you, if you spent time looking at the people around you and thought about the fact that memory is a reconstructive process, you'd look at some of these people and think, I think you need to go back to the drawing board because I think you're making up some of that stuff. And the thing is that they're not lying. They don't really know they're doing it, but it's happening. Okay, finally, I want to tell you about psychogenic fugue, and this is going to be extremely quick. But psychogenic fugue is a kind of, it's more an emotional disorder than a physical brain disorder, but it is brought on by physical trauma to the brain. But what happens in psychogenic fugue is an emotional shutdown. And that emotional shutdown means that the person effectively doesn't know who they are. And there have been cases of this, and some of you may remember this case from 15 years ago of a young man dressed in a black suit, white shirt, was found on the Kent coast. He didn't know who he was, didn't know his name or anything like that. When he was taken to a nursing home to try to help him, he wasn't even speaking, but at some point he went into the recreation room where there was a piano and started playing the piano. And what seemed to have happened is that some sort of trauma had happened to this young man and his brain had switched off and his brain didn't know who he was, etc., etc. This again is extremely complicated, and if you remember the graphs that I showed you at the beginning about the number of papers on psychogenic fugue, you'll remember that there are hardly any papers. So it's very difficult to do research in this area because of the rarity of the disorder. But what this type of disorder shows us is that our brains are doing something to help us cope with everyday life. And sometimes an emotional shutdown means that we actually lose sense of who we are ourselves. Okay, so to summarize, the analysis of rare disorders gives neuropsychology this incredible insight into very specific aspects of cognitive behavior, so the mental processes that we use every day, such as memory, language, etc. And some disorders demonstrate fundamental aspects of how we all function. So the split brain syndrome, and that the fact that one hemisphere does one thing, the other hemisphere does something else, and the corpus callosum moves information between the two of them to help us get a unified view of the world. But then other disorders such as Capgras and Confabulation, they give us insights into fundamental aspects of our lives that we take totally for granted. So the Capgras shows us that we have an emotional reaction to people when we see them, a reaction which is a recognition, but it's an emotional recognition. And that is for people that we care about. And when that's stripped away, if we see those people, if we have this condition, then we think that our loved ones have been replaced by imposters, even though David in that video knew that that sounded completely mad. That was his feeling. And the confabulation shows us that memory is not this looking at a series of pictures or a series of videos of your life and picking out the right one and just playing it back. It's you recreating what could have happened, and that sometimes that can go wrong, and it can go really wrong because of certain types of brain damage and cause this disorder called confabulation. So as I said, there'll be a second part, which will be in 2 weeks' time. And in that second part, I'll tell you about visual neglect, phantom limb syndrome, not phantom limb syndrome, excuse me, alien hand sign, and Cotard syndrome. So that information will be shared with you through my mailing list, etc. Finally, I just want to tell you about the studies that we're doing in some of these areas. So these are things that I've mentioned in previous talks. One of the biggest studies we're doing is on memory, and we've developed a test which we hope, we think is able to detect preclinical signs of dementia. And that's extremely important because dementia is extremely prevalent across the world, but it's usually diagnosed when it's too late, because it's a subtle, insidious disorder that comes on very slowly. And what we're trying to do is to develop a test to diagnose it much earlier, and in that way you can help the patient and their families much sooner. And I'm actually coordinating an international project where we're translating the task into as many languages as we can. And currently we've got, I think, 5 or 6 languages that we're working with. So if you're working in the area of dementia and you're abroad, please do get in touch with us, because we'd be very happy to have you on our international collaboration. In the face recognition world, we're looking at both developmental prosopagnosia. So this is prosopagnosia where there's been no brain disorder, brain damage, but these individuals have always had difficulties with recognizing faces, but also acquired prosopagnosia, which is much more rare. So that's my patient, David, who was in that video with me, who can recognize his wife. So that's an area we're working in. Another area which Claudia, my student, is going to be doing her PhD in is that looking at prosopagnosia in children, because most people only realize they've got developmental prosopagnosia when they're adults, and they hear a nerd like me talking about prosopagnosia and they realize that maybe they've got this condition. But through childhood, they've had difficulties at school in terms of recognizing their friends, their teachers, etc. And they always just thought they were a bit weird. And there are all sorts of behavioral things that they do in terms of stepping back from things because they think that they're different. And what we'd like to do is to help diagnose prosopagnosia much earlier so that we can help these kids. Last week, I talked about executive functions on the front of the brain, and I told you about my assessment, Jeff, the Chinsari assessment of executive functions. And it's a computerized test which we're using to look at how the front of the brain helps us make decisions, plan behavior, etc. And we're looking at traumatic brain injury in adults. We're looking at development, healthy development through childhood and adolescence, a whole host of developmental disorders such as autistic spectrum disorder, attention deficit hyperactivity disorder, developmental coordination disorder, and looked after children, and other developmental disorders as well. We're also looking at the impact of drugs, both recreational and drugs for cancer therapies. And then an exciting project, which is the involvement of childhood head injuries in later criminal behavior. Then Pedro, he's doing research, not with me, but with one of my colleagues on stroke rehabilitation, and looking to see how we can use music to improve movement rehabilitation when someone has got brain injury that's resulted in some sort of semi-paralysis. And Pedro is using music to try to help these people gain some movement back. Okay, to get involved with any of our research, either as a participant, because we're constantly looking for people to do our research studies, or if you want to know more about our research and actually contribute by being a collaborator, then please do get in touch with us. So could you write to Claudia at c.pulcini@gold.ac.uk. So finally, it just leaves me to thank you for your patience and the technological problems that happened, and for tuning in. The next talk will be about memory, amnesia, and dementia. And as I hinted, memory is an extremely complex disorder. So I'm going to tell you about things that we know about regular memory, and then about amnesia from studying patients with the very severe forms of memory problems, but then move into the thing that I'm now doing more and more work in, which is dementia, and how we can try to develop better tests to catch dementia earlier than is currently possible. That will probably be happening next Saturday at 5 o'clock as well, but I will confirm that soon. Okay, so my first question is from Felicity Sykes, who's asked, does split brain make learning to play the piano easier or harder? Not a clue. I forgot to mention some of the statistics on this because they're difficult to get, but Felicity, and everyone else for that matter, the thing is that there are only about 60 patients in the whole world who've had a full corpus callosotomy, where the corpus callosum has been cut completely. So 60 people in 7 billion. So it's extremely rare, and so I don't know if anyone has asked them, is playing the piano easier, etc. There are some things that they find easier, but since it's a very rare disorder, I wouldn't know. This is the sort of thing that if one worked in that area, then it would be possible to try out those experimental questions, but I don't know, I'm afraid. But if I ever find out, I'll let you know, Felicity. Next question is from Barbara Georgelis, and it's about the unconscious recognition and prosopagnosia graph. Did they investigate why there was a difference in these two patients? Patient 2 feeling less familiarity with family members is interesting. Yes, so Barbara is talking about this on the left-hand graph here. You've got patient 2 is finding unfamiliar people, so Joe Blogs, 5 out of 10 interesting, not interesting, sorry, familiar, whereas the finding family members only 1 out of 10. I have no idea whether they did this. I imagine that they probably did, but there wasn't any convincing explanation. Now, the thing here is that with patient research, with single cases, it's very difficult to know for certain, because these two people have had brain damage, and the brain damage will be different in the two patients. So we're not comparing like for like when we look at patient 1 and patient 2. They'll have different areas of damage, etc. So it's probably to do with different extent of brain injury. But also the other thing is that sense of familiarity is a measure that some psychologists use, where they say, okay, on a scale of 1 to 10, how familiar is this? Now, that is not a kind of gold standard way of doing testing. Whereas with the galvanic skin response, the person has absolutely zero control over this. Sense of familiarity depends on how I define the term, how you define the term to yourself, and interpret it, and therefore what is a 5 out of 10 to you might be a 3 out of 10 to someone else. So this measure, it's one that they use just to get some idea of what was happening, and mainly to show that these people were saying that their families didn't look familiar to them, and how this contrasts with the galvanic skin response here. But why this patient was different to this one, I don't think we'd be able to answer. I might actually look at the original paper and see whether they did, but I don't remember seeing anything that suggested why. And Rosie Ball has asked, is lack of awareness a bit like blindside? Oh, Rosie, I haven't lectured about blindside for about 20 years, so I'm going to have to try to make this one up. I'm going to have to confabulate, I think. So blindside is this rather rare disorder, they're all rare, where these individuals have got a certain level of blindness, but it's not complete blindness. So you can have a patient who's blind to what's happening in the left-hand side of the world because the brain damage in the right hemisphere is such that they're not seeing it. But what's seen in some of these patients is that although that brain damage over here in that visual area where the cat, if you remember my first diagram, one of my first diagrams where the cat is first seen, so that area of the brain is damaged. So they're saying, yeah, don't see anything. But they have a response as if they have seen something. So they'll walk around something that they say they don't see, and that's known as blind sight. So blind sight is this really rare disorder discovered by an amazing scientist called Larry Weisskranz in Oxford. And it tells us something about how there are different layers of processing. And in a way, it's kind of like the Capgras Syndrome, where the face recognition is happening at a number of levels. There's that conscious level along the floor of the brain, but then there's that emotional recognition that's happening a bit further into the middle or older part of the brain. So maybe blind sight is giving us an insight into the fact that there are what we refer to as parallel processes going on. So three things happening at the same time, or two things happening at the same time, such that you can lose the one to actually see the object consciously, but still have an awareness that it's there. So I think that there are parallels there. I hadn't thought of it like that. So thank you for making me think like that. Emily Elliott asks, so is Capgras visual and not emotional neural pathway? So yes, effectively what Capgras is where this is the visual pathway, the red one going along the floor of the brain, and the emotional one is this one here going through the middle of the brain. And Capgras involves a damage to the emotional recognition, leaving the visual recognition okay. So this is why we get what's called a double dissociation, where we have the patients with prosopagnosia who say, I don't know who this person is, but there's an emotional reaction to them because they've got damage to the visual recognition system, but their emotional one is intact. And then the Capgras patients, they're the opposite. Their visual recognition is saying, yeah, this looks like my mom. Their emotional reaction is saying, I don't feel anything for this woman, so it must be an imposter. Okay, Mandy Wood has said, I'm watching with my 15-year-old. Hello, Mandy, you should have told us what your 15-year-old boy's name is, so I could have said hello to him. But hello, 15-year-old Master Wood. And she said he wants to know a bit more about photographic memory, please. So photographic memory, also known as eidetic memory, is this... It's somewhat controversial. There is a suggestion that when we're younger, we all have quasi-photographic memory, that we visually just see things and we kind of store these snapshots of what's out there. And that what happens is that as we go in through childhood, as our memories form and become what we now as adults know of as human memory, that we lose that ability. And so it's kind of that process of losing the ability to take those photographs, like you saw in that video of what's happening with memory distortions, and now instead encoding it and creating your image, and that storing that, and later on trying to find a way to recreate that. And what we think is that maybe with children, that ability in those early years is more the snapshots, which is the photographic memory. But then as we get older, we lose that. And that maybe with these HSAM people, there's more of that process still going on. But as I showed with my skepticism, I don't think that that it's complete photographic memory. So I hope, Master Wood, that helped. Priyesh Patel, I wonder whether that is the Priyesh Patel that I was at school with 35 years ago. Prayesh has asked, is there a way to train memory to become better? Yes. And I would, for this, just take you to my graph of we're not all the same. Lots of people are in the middle here. Some people are poorer, some people are better. Now, if we take an ability like running, you could be an average runner, and if you train, you could become a higher than average runner. And if you're like a club level runner and you really train, you could become a national level runner over here. So in that way, because memory is a skill, we can improve that. So we can improve anything, just in the way that you can improve your piano playing or your cooking or anything like that. Memory being a skill, it can be improved. The thing we can't do is to turn everyone into these HSAM people, and we can't all become amazing and remember everything in our lives. So memory can be improved, and I think that's one of the things that a lot of researchers are trying to do, is to find ways to improve our memories, to help our parents, etc., so that their memories don't start fading. So yes, it is possible to improve memory, but it's usually kind of incremental steps towards the right. It's not a case of becoming a super memory person. Okay, next question. Joe Marshall has asked, do you think déjà vu is similar to these disorders, something to do with the activation of the emotional pathways? That is an interesting question. There was work a few years ago that I heard of about déjà vu. So those of you who don't know what déjà vu is, it's this idea of, I've already seen this, this has already happened. And we all get fleeting moments of this, of, I think I've seen this already, or haven't I heard this before? And sometimes we have heard it before, but sometimes we haven't. Now, I don't really know what's happening with déjà vu. One thing that I had heard, but I'm not going to, put my mortgage on it or promise anything on this, but I think that there's involvement of temporal lobe epilepsy in cases of déjà vu. So these areas here, which are visual recognition and recognition of events and our memory system, these areas are really important for that. If you've got epilepsy, then it does affect the way we remember things and the quality of what we remember. And if you remember, I talked about the patients with the Fregoli syndrome for whom everything seems familiar. So that sense of familiarity is a kind of déjà vu. Yeah, I've seen you before, even if you haven't. So I think that there is something going on there with hyperactivation of the temporal lobes. But I kind of made that up on the fly. So I hope some of it made sense, that some of it was actually accurate, but I don't work in it. Okay, Caroline Bloom. Hello, Caroline. Dr. Caroline Bloom, GP. Have any brain abnormalities been found in transient global amnesia, which tends to only last a few hours? So transient global amnesia, for most of you who won't know this, is a form of a memory problem where a patient has this complete kind of blackout, and hence the global, but it's transient. It only happens for a couple of hours. So it's a kind of shutting down of the system. In terms of brain abnormalities, I imagine there will be, and I imagine they'll be in our old friend, the temporal lobes, because those are the memory centers. There are people that I know who work in this area, and I'd be very happy to find out information for you. I don't know off of the top of my head or off of the top of my temporal lobes what the answer is in terms of the physical abnormalities, but I imagine that if there's anything going wrong in amnesia, in memory, these guys are at fault. So it's something to do with temporal lobes. So if you do want to know, I will answer you properly. Jen Good has asked, can you confirm the name of the area in the brain responsible for the emotional responses that help us recognize very familiar faces when you were talking about prosopagnosia and Capgras? The names of the areas, it's a pathway known as the dorsal pathway. So it's not one specific area, but it's the dorsal pathway going through an area called the limbic system and the amygdala, which is really important for memory, but it's not one specific spot. It's a whole pathway. But if you look up Capgras syndrome and a name, Hayden Ellis, Haydn Ellis, ELLIS. He's the person who's published in this area, and it was his figures that I'd stolen. So if you're particularly interested, you can find that out by looking at Hayden's work. Okay, Sophie Brown has asked, are there particular types of brain injuries that cause Capgras? Only ever seen one, which was TBI from car accident. Okay, so TBI is a traumatic brain injury. Very interesting question there, because Capgras has been found in lots of different conditions, and just recently I found out that Capgras also happens in the context of dementia. So there are people who start claiming as a part of their Alzheimer's or other dementias that someone has been replaced by their imposter, by an imposter. So it's not them forgetting a person or their home, but actually saying, yeah, you look like so-and-so, but you're not so-and-so, or this looks like my house, but it's not my house. So Capgras can happen with other disorders as well, such as Alzheimer's. I think the clue is in your question, which is TBI. So traumatic brain injury from car crashes usually involves this. I shouldn't keep doing that. It involves a knock to the front of the head. Now, the reason that that's important is that the front of the head is, as I explained in my last talk, it's the brains of the brain, and it's the one that makes sense of everything. Now, if that part of the brain is getting impoverished information, then, and it's damaged, then it's not playing with a full set of cards, as it were. And so it has to try to work out what's happening. And I think that in the case of that young man, David, who'd had the car crash, so just like the patient you've seen, presumably clinically, there's a car crash, and the car crash will have hit him here, and it probably had damage further into the brain as well. And I think that you've got those two areas of damage, the one in the emotional pathways and the front of the brain. Because I think what happens, and again, this is a just conjecture, but I think what happens is that with the lack of the emotional response, but with the visual recognition from the floor of the brain saying, yeah, this looks like my mom, but without that warm, fuzzy feeling, there is a kind of mismatch. Now, if the front of the brain was completely okay, then the front of the brain might be able to evaluate that and say, okay, right, so this feels a bit weird, but it can't be an imposter, it's my mom. But if the front of the brain has got a problem in itself, and it can't evaluate the information that it's receiving, then this strange delusion comes out. Now, if you, I'll make an analogy there with the confabulation, because with the confabulation, we've got a similar thing happening, that those processes that I said, which generate this, what could I have done on the 12th of February 2010, that is coming from our temporal lobes, and it's creating what could possibly have happened. And then that's sent to the front of the brain, which is the one that packages it up together and then outputs it as a memory. And what we think is happening is that that part of the brain, that damage in the front of the brain is meaning that this kind of gobbledygook that's coming out because of the damage over further back it's not being evaluated as gobbledygook. Whereas if you thought that you were this command of the space shuttle, there's a part of you, an intact front of the brain, which would say, haven't done astronaut training, so I don't think that's likely. So I think that it's that combination, and that the damage in the front of the brain is contributing. And I think the fact that we're seeing it in Alzheimer's as well, and the fact that in Alzheimer's there's a lot of damage, degenerative damage happening in the front of the brain, is an extra clue to the fact that that's probably why it's happening. Okay, my next question is, right, so it's Avril, who I think is in Dublin, has said, she had a 14-year-old after head injury. He could look at a picture, simple line drawings, and then when given a prompt to redraw, he would add in all these details that he decided must have been there. He'd have the lady waving, for example, because why else would she have been stood on the quayside, and give her a hat because the picture was outside. Knowing he would not look on him, but he would make up a little story, but the details were not in the visual at all. He had better memory for voices and story detail he had heard, but his recall of visual information, even 7 to 8 years later, is never reliable. Okay, so Avril is basically saying that when he was shown these simple line drawings, he would come out with these fancy stories of what it represented. That's quite interesting. So it sounds like a visual form of confabulation, that he saw these line drawings, a cube or something like that, but when he was recalling it, he was trying to remember what it was, and just like the patient RY, the one that I worked with, who thought that he was the commander of the space shuttle, he's recreating that information, but the recreation is going wrong and getting really fanciful. Now it's interesting that it's a visual happening only on the visual side of information, because what I would conjecture then is that the kid probably had damage on the right-hand side of the brain, because RF, the space shuttle confabulator, his damage was more on the left-hand side, and the left-hand side is more verbal. The right-hand side is more visuospatial. So I think that the damage in the visual spatial hemisphere here, plus that confabulation, just like with the previous question that I just answered, I think that combination of right hemisphere damage and the damage in the front of the brain resulted in a confabulation to do with visual information. Again, it's a conjecture. Next question is from Denise Apsi, which is that, is there any evidence that the brain can rewire itself to overcome some of these issues, like prosopagnosia, for example? Not really. There is evidence of some rewiring of the brain, but it's very complex, and the rewiring is not going to bring back what you already had. So there are two different levels to this, or a number of different levels to this, whether rewiring is possible or not, and there is some rewiring that can go on. The second is, even if the rewiring happens, whether that gives you back what you had before. And then a third element to it is that the brain is more plastic, so it can change more when we're children. So there's probably more neuroplasticity, so the ability of the brain to repair itself when we're younger than when we're older. So I think the mantra is that if you're going to have brain damage at some point in your life, it should be when you're younger. But what we're now finding, as I demonstrated in my talk last week, is that early brain damage then results in downstream problems later on in life. They're a bit different. So the same damage will impact a child and an adult differently. So it's difficult to give a complete answer. What I would say is that brain tissue is very different to other tissue. And I'm saying that without any real knowledge, apart from the fact that we know that it's possible for you to graft skin from one part of the body to another, and that skin or that bone arrives in its new home, and after a bit of, oh, I feel a bit lost here, it kind of feels at home and it just behaves like it's always been there. There's no evidence whatsoever yet of that happening with the brain, which is why grafts of brain tissue, etc., haven't, well, they've probably been tried, but there's no evidence that it works. So I think the issue with neuroplasticity and rewiring is that even if it happens, we're not going to get back to what it was before, and that is always going to be a conundrum. Whether it will never happen is a separate issue, but at the moment there isn't any strong evidence of that. Interestingly, your question, however, does dovetail into one of the issues that I'll talk about in 2 weeks' time, which is the phantom limb syndrome, because the phantom limb syndrome is about people who've had an arm or something amputated and they feel that arm even after the amputation is gone, and they sometimes feel a lot of pain in it. Now, that is actually to do with rewiring, but the problem is that that rewiring isn't the rewiring that we'd be referring to for getting back the function that we did have. So yes, no, maybe, and sorry is my answer. Okay, there's a question from one of my people in, or not my people, but one of the people I know who's following us from Greece. I'm sorry, because I can't read the Greek alphabet. I can't say your name, but I think you know who you are. And this person has asked, how are the ORB, which is the own race bias, and memory for emotional recognition correlated? So the own race bias is something I talked about a couple of weeks ago in the face memory lecture, which is the finding that generally speaking, we tend to be better at recognizing people from our own ethnic group than people from other ethnic groups. Now, that itself is actually it's nothing to do with biology. It's simply to do with the fact that we tend to grow up around people who look like ourselves. And because, almost linked to Priyesh's question earlier about whether we get better, whether we can train memory to get better, when we're young kids and our face recognition system is developing, we're getting better at face recognition. It's a skill that we're getting better at, but the faces that we're seeing are generally of our own race. And that's why we become really good at recognizing people of our own race compared to people of another race. However, if you grew up in a family where all of the races of mankind are represented, and all of the people around you were of all the races of mankind, then you wouldn't have the own race bias. So the own race bias is simply because, by and large, unless you live in an incredibly ethnically diverse home and an ethnically diverse environment, you will be seeing more people of one race than another. How this is linked to emotional recognition, I don't know. And I think the only correlation here, I might be wrong, but the only correlation here is that familiarity results in a kind of a greater emotional safety, whereas when you're around people that don't look like you, you can feel a bit like I'm out of my comfort zone. These people look different to me, etc. So you can draw in and feel like the odd one out, and so emotionally feel different. So I think that's the only way I can see the two things would come together. Otherwise, I can't see how the own race bias and emotion are related to one another. Okay, I'm just looking to see if we're done with questions. I'm just going to ask my team whether there are any questions. Could one of you just let me know? Otherwise, I think it's nicely just before 7 o'clock, which means that I can go outside and have a socially distanced glass of wine with Anna. So, team, are there any more questions? Get in touch with Claudia or myself if you either want to get involved in research. I know that there are a lot of school teachers that are listening in, and I do a lot of research with school children on various projects, the memory one, the face recognition one, and the executive functions one. And so we're always interested in partnering up with schools to do research, and some of this can be done just online rather than physical meetings. I know there's some clinicians out there as well, so if you're interested in talking to me about research collaborations, do get in touch with me. But if you're just interested in our research and just being a participant, then please do get in touch, and we'll send you our test by email. So thank you again. Next talk, memory, amnesia, and dementia. Do spread the word, and hopefully I'll be outside having a glass of wine soon. So thank you very much, and good evening.